derived, which is the output over the input, which is this equation, the Bode plots can be created. So there's two plots for the Bode plot. You have the magnitude, and the magnitude is in what is called dB. And you also have the phase plot, which will be in degrees. So we're going to first look at the magnitude plot. So the magnitude means that we're just going to physically take the magnitude of the transfer function VO over VI. So taking the magnitude of this function, the magnitude of the top portion is going to be times j omega, and then I'm going to plug in s equals j omega also on the bottom. And the magnitude of the top is going to be 133 nano times omega. And on the bottom, you have an imaginary number, and you have a real number. And the magnitude of that, if you recall, is the square root of the imaginary squared plus the real squared. So the square root of the imaginary portion, which is 266.7 nano, times omega, that's all going to be squared, plus the real part, which is 1 squared. So now this is a function of omega, and I can plot this by hand by plugging in values of omega from some small number, 0.1, to a large number. I could do 10 megs. And for each omega put in, I'm going to get a magnitude value, and it's going to be a dot on the graph. So to do the phase, I'm going to do the same thing, except for I'm going to take the phase of this transfer function. So the phase of V out over VI this time. Again, I'm going to plug in j omega. So I have 133 nano j omega on the top, and the 266.7 nano j omega plus 1 on the bottom. So the angle of the top one is going to just be 90 degrees. Remember, J is a 90-degree vector with the magnitude of 133n times omega. So looking at only the angle, I have 90 degrees. And on the bottom, the angle is the inverse tangent of the imaginary number over the real number. In this case, the imaginary number is 266.7 nano omega all over 1. And if you recall from angles, multiplying angles means that you add them. If you have a divide, then you subtract. So we can take the top angle, which is the 90 degrees, and the inverse tangent, which is a function of omega. And this will be our phase graph. Point on my graph. Then I do another dot, and then I connect them with a line. Another way would be to take Excel and use Excel to plot each one of those, which is going to be a little quicker. It was 90 minus, just so I can remember. So it was 90 degrees minus the inverse tangent of 266.7 n times omega. So, and this was the transfer function of the magnitude was 133n times s over 266.7n times s plus 1. And the magnitude function, that was the transfer function. The magnitude function was 133 nano times omega divided by the square root of 266.7 n omega, that whole quantity squared, plus 1 squared. So what I'm going to do here is at the magnitude, well, first off, I'm going to put in a whole range of omega. I put them from 0.1 all the way up to almost, or approximately 1 times 10 to the 9th. So a big range of those. I've plotted, so those are the radians per second. This function in the transfer function has the values of radians per second because it's in omega. And then the magnitude is in volts per volt. It's a dimensionless quantity. And then we want to translate that into dB, and I'll show you that in a second. So what I want to do is MATLAB, I already know MATLAB will plot this in radians per second. So I'm going to plot the Excel in radians per second. But PSpice will plot it in hertz. So I want to change all the omegas also to hertz, so that I can do a comparison with that also. So in my magnitude, in volts per volt, I'm going to just take this magnitude equation, which was 133 e to the minus 9 times, in this case, this is my omega. And I'm going to divide it by the square root of the 266.7 nano times that omega again. And that quantity is squared plus 1 squared. And I'm missing a parentheses in here. And then I have my volts per volt. So I can copy this and drag it down for the rest of those values, and it will automatically do that. And then I want to change each one of these volts per volt into dB. The translation into dB is 20 times the log base 10 of the volts per volt. So now I can copy these down also. And now the degrees, I'm going to take the 90 degrees minus, I need to use the function called degrees in here to convert the radians per degrees, because the function atan, which is the arctangent of a number, returns it in radians, and I want it in degrees. So atan, and then 266.7 e to the minus 9 times that omega, and it was over 1. So this gives me the degrees in for the phase. And now I have these values, I can use a scatter plot to plot them. So I'm going to highlight, I'm going to do this first in radians per second to compare to MATLAB. So I highlight this, use the control to highlight the dB column, and then I'm going to use a scatter plot, and I can do a continuous scatter plot. And then I'm going to change this axis So whenever you plot a Bode plot, it's actually on a semi-log graph. And that is done by the x-axis being a log scale. A log scale is always in a base of 10 for us, so just make sure you click log scale on the x-axis. And this shows you now the x-axis. I'm going to just move this to above the axis so it's a little easier to read. And now I have the magnitude plot. I can again highlight the hertz and do this in hertz along the x-axis. Now I want to plot the phase, so I'm going to highlight my x-axis again, and then to do the degrees, and again go back to the scatter plot, continuous one, and then change the axes. I'm going to add the minor grid just so that I can see it a little easier, and then change that to a log scale on the x-axis. I'm not sure what that second one was, so I'll highlight these again and repeat that. So mega radians per second, and the phase, scatter plot, and change this to show the minor axes and give me the logarithmic scale on the x-axis. And this concludes drawing the Bode plots, which was the magnitude plot up here, which was the magnitude with the x-axis being omega in radians per second. The y-axis is in the magnitude in dB. And then I had to change this x-axis to be a log scale. That is the standard form for Bode plots. And also down here, the phase in degrees on the y-axis, omega is radians per second on the x-axis, and the x-axis is a log scale. This concludes plotting using Excel.